Literally. Yesterday we started with power roll. I want to do a little bit of review, and then we're going to move into position, velocity, acceleration. Some of the homework problems. Well, first off, our class is cut short a little bit today, and some of the problems that I assigned you, we're going to do tomorrow. So I'm actually going to let this tonight's homework be due on Monday. But you're welcome to start on it, but I won't check tomorrow. I'll check on Monday. We'll go through some of the other. Actually, 97 through 100. We'll try to spend some time on those problems so we can do them in class. Okay. But in your packet, if you guys can turn to page 12, I just want us to do a quick review of power roll, and then we'll go into our today's lesson. Okay, so page 12. We're just going to try number 9 and 10. Okay. So with power roll, it's a lot more efficient way of finding derivative than the limit definition was, but we do lose that visible connection with slope formula. But hopefully we've been saying it enough where we just continually remind ourselves that derivative is just a fancy word for slope, and it's adapted to adjust to the changing slope of a curve. And the way that we go through power rule is if we start off with x to the nth power, okay, we bring that exponent down first, and then we take the existing exponent and subtract 1 from it, okay? And that's going to be your derivative. So this is going to be the derivative rule that you're going to use more often than any other derivative rule, but it does come with its conditions. Okay, so it's very easy to use it incorrectly and therefore arriving at the incorrect derivative. So first is make sure that you're converting your radicals to rational exponents. It allows you to see that numeric value a lot more clearly when you do that. And second, make sure that your denominator variables are brought up to the numerator before you apply power rule. If you try to do power rule with a variable in the denominator, it's just not going to work. So this is meant for x to the nth power in the numerator, not for x to the nth power in the denominator. And third, all your parentheses have to be resolved. So if there's any variables that needs to be expanded, combined, we need to do that. Okay, and we're going to see that especially with number 10. So number 9, g of t equals t squared minus 4 over t cubed. We have 2 terms. They're nicely separated, so really we can treat them like individual terms, individual problems. But we do have to do a little bit of a rewrite. So the first term is fine, t squared. What adjustment do we have to make with the second term? Okay, move that t up to the top. We can't just leave that below and call it 3t squared. Okay. We have to bring it up to the top so that we can actually see the true exponent that will be used for power rule. Okay. So now that everything is nicely cleaned up, we can apply power rule. So derivative g prime. T squared becomes 2t. Right? We bring the 2 down, subtract 1 from the exponent. Minus. Bring down the -3, and then subtract 1 from the exponent. Okay, so there's our derivative. We just have to do a little bit of a cleanup. Two negatives become positive. And then finally, we can bring that. So we have our derivative, but I am going to ask you to do some cleanup here. So we'll bring that t back down to the denominator. However, that -4 only impacts the t. The 12 is going to stay up in the numerator. Number 10. 4x cubed plus 3x squared all over x. That x in the denominator kind of makes things difficult for us to see things clearly. So what can we do to handle that denominator? Yeah, let's make it into two separate fractions. And then we can treat it like two separate problems rather than one mess of a fraction. Then we can individualize each term, clean up each term. Two ways that we can do this. You can bring that x up to the top and make it x to negative 1. Then you can add exponents. Or maybe it's easier to just think in terms of just reducing and canceling out, right? There's 3 x's here, there's 1 x here. I can remove 1 from both. Here I can remove 1 x from both, and that will take away my denominator. But sometimes you do want to go through this process, especially if the fractions are not as easy to reduce. If they're fractional exponents, then I typically want to move it up and then just go ahead and subtract. So 3 minus 1 is 2. 2 minus 1 is 1. Now that we have each of the terms separated with no division, with no variable in the denominator, it passes all 3 conditions. We know we can find our derivative with no issue. So notice that every degree is going to drop by 1. So 2 turns into 1, 1 turns into nothing. Yeah, and this derivative, the job of the derivative is to describe the slope behavior of this original graph. Whatever this original graph looks like, this is going to be able to describe it. Okay. Okay, there's some more review that we can do, but I really want to be able to start on today's lesson. So let's go to page 15. Okay, so notes on position, velocity, acceleration, PVA. So far, we've seen the relationship between f and f prime. We know that given the original function, we can find the derivative. We know the derivative is going to describe the slope behavior of the original function. We can also think of the derivative as a way of describing the rate of change of the original function. Okay, so rate of change, slope, derivative. We were going to use those 3 things interchangeably a lot. But we can even go one step further. We can find the second derivative, and the second derivative, f double prime. We can think of this as the rate of change of the first derivative. One particular relationship between these 3 functions that makes it more concrete, even though it doesn't mean that every relationship that we're going to have is going to be position, velocity, acceleration. But we're going to be able to have that relationship here. So we can think of the original function as the position function. And then we can think of the velocity as the derivative, because velocity is the change in position over change in time. So velocity does describe the derivative or the rate of change or the slope of position. And then the second derivative is acceleration. Nice thing about acceleration is that it is a concrete way of visualizing what the second derivative does. Acceleration is the rate of change of velocity, but it's also the rate of change of position. Okay. So we have specific notations though for position, velocity, and acceleration. Typically position, you may see P of t or H of t or S of t. For velocity, we typically use V of t, and for acceleration, we typically use A of t. So instantaneous velocity, v of t, is the derivative of a position function with respect to time. So the word instantaneous means velocity at a specific moment in time. And we use v of t to represent that, but we can also use s prime of t, right? The derivative of s of t, we can represent as s prime. So we have different ways of representing the same function, just depending on where we start and our frame of reference. Acceleration is the derivative of velocity. So we can represent acceleration as a of t. We can also think of it as the first derivative of velocity, so v prime. But we can also think of it as the what? Yep, second derivative of position. So we use s double prime of t. Okay, average rate of change is the slope of the secant line. Slope of secant, that just means a line that goes through 2 points of the curve, and we're just trying to find that slope. So slope of secant, if the graph looks like this, then a secant is just a line that touches through 2 points, right? A tangent line is one that just skims the surface of the curve at 1 point. Now, average rate of change, a common, and we're going to talk about this, if not today, then tomorrow, is a common application is average velocity. Average velocity is the change in position over a change in time. Now, average velocity is meant to tell you over a period of time, right? It's not a velocity at a specific moment in time. It's just the average velocity over a period of time. So for instance, let me just make a distinction here. Let's say you go on a road trip, and that road trip covered 300 miles. Okay. And you knew that it took you 5 hours to make that trip. Then what is the average velocity of your trip? 60 miles per hour, right? Which means that if someone is driving 60 miles per hour straight for 5 hours, they're going to reach 300 miles. But does that mean that you're traveling at 60 miles per hour the entire time through? No, that's just your average, right? That's just your average velocity. It doesn't mean that you're always traveling at that speed. Now, the difference with this versus instantaneous velocity would be if someone were to ask you, okay, how fast were you traveling exactly 2 hours into the trip? It could be 50 miles per hour, it could be 75, it could be 65. So a moment in time versus an average, that's the distinction. Okay, we're going to talk about that. One requires calculus. This one does not require calculus, right? This is just really just taking 2 points and finding the slope between them. Okay. All right. Let's see. Moving on here. Yeah, instantaneous rate of change is the exact slope at that moment in time on the curve. Speed is the absolute value of velocity. So velocity has direction. So if something is traveling at negative 20 feet per second, your speed is going to be the positive version of that number. It'll just be 20 feet per second. So for instance, if velocity, example, if velocity is negative 20 feet per second, the speed would be the positive version. And if velocity is positive, then your speed will remain the same. It'll be positive as well. So the only time your velocity and your speed will be different is if velocity is negative and you're forcing the speed to be positive. Okay, displacement. Displacement is how far you are from where you started. But distance is the total amount you have traveled. So distance and displacement are very much one and the same unless there's backtracking involved. So if someone's traveling back and forth between two, backtracking along their path, then their distance will be further than their displacement. Okay, so here's an example. If I travel 10 feet to the right, and then turn around and travel 3 feet back, or 3 feet to the left, my distance is 13 feet because I traveled 10 plus 3, but my displacement is only 7 feet because compared to where I ended up and where I began, I only made a forward progress of 7 feet. Okay, we're going to try to get to these topics. If we don't, we can cover tomorrow. But the idea is that speed is increasing. We can say that the particle's speed is increasing when the velocity and acceleration have the same signs. So if velocity and acceleration at that moment in time are both positive, or if they're both negative, then we can say that the speed is increasing for that moment in time. Speed is considered decreasing when the velocity and acceleration have opposite signs. Okay, so if one is positive and the other is negative, then we can say that the speed for that particle is decreasing. For particle or for position, velocity, acceleration, we also have a very similar thing, which we call particle motion. And whenever you see particle motion, it just means that this particle is going to be moving in a very restricted manner. It's going to be moving along a linear motion, usually along a horizontal line. So for instance, if an object is somewhere on the x-axis, it can only do 3 things. It can only move to the right, it can move to the left, or it can remain motionless. So a lot of position, velocity, acceleration is still going to apply. We just have a more restricted motion for this object. Okay, so I'm going to have you guys copy this down here. We usually represent position as x of t. So you're going to see that there's a lot of variation for position. Sometimes you may see x of t, s of t, p of t, h of t. Okay, so but usually velocity, acceleration kind of just we rely on just those distinct variables. Okay. So have you guys write this down here. Positive velocity indicates a particle is moving in the positive direction, and usually that is to the right. Okay, so when we talk about particle motion, we're usually talking about moving horizontally along the x-axis. Negative velocity indicates when the particle is moving in the negative direction, usually to the left. So we associate right with positive and left with negative. And then when v of t is equal to 0, this indicates that the particle is at rest or motionless. And something that we're going to discover later, especially with the next unit, is that when a particle is at rest, that a lot of times is an opportunity for the particle to potentially change direction. So we're going to talk about later, like, oh, how can we tell when the particle is going to change direction? We look for when the velocity is 0, and then we look at that as a candidate for potentially a particle changing direction. So if the particle is going to change direction, it's moving left and right, it's got to have at least that moment of motionless moment right when it changes direction. Doesn't mean that when the particle is at rest that it will always change direction, but it is a prerequisite for a particle to change direction. It's got to come to at least a moment of motionless. Yes.
What's the word in the red? It says opportunity and then
for the particle to change directions. All right, let's go to the next page. And we'll try to get through this full extended PVA problem, but if we don't, we'll just pick this up tomorrow. Okay, so about 20 minutes here. Does anybody still need this page here? Okay. Okay, so let me read this problem here. A ball is thrown vertically upward from the edge of a building, and it eventually hits the ground next to the building. Okay, so we're just going to draw a quick visual here. You have a ball that is at the edge of the top of the building, and it's being thrown vertically upward. And eventually it's going to make its way down and hit the ground. If the height of the ball at any given time, where t is greater than or equal to 0, is h of t, then answer the following. Okay. So h of t is representing position function. So I'm going to have that here. So h of t is going to do the job of telling us the height of this ball at any moment in time. So if I give it a t value, whether it's 0 or 1 or 2 or 3, in return, it's going to give me a number, and that number is going to tell us how high the ball is off the ground at that moment in time. So h of t is my position function. Let's go ahead and find our velocity and acceleration function just to get the calculus out of the way. And the rest of it, we're just going to be using it and interpreting it. So the nice thing is that all these terms are set up and ready for power rule, right? There's no radicals to convert. There's no variable in the denominator. There's no parentheses. So we can jump directly into power rule. So first term, what's the derivative of negative 16t squared? Negative 32t. 64t turns into 64, right? So degree 1 is going to turn into a constant, and the 80 is going to go to what? 0. Good. 80 is a constant. It's going to go to 0. The slope of a horizontal line is going to be 0. Okay. So let's talk about the role of velocity function. So velocity is going to tell us the rate of change of the change in position over the change in time, but it can also tell us the specific velocity at any given moment. So if I give it a t equals 0, that means if I want to figure out how fast is the ball moving 3 seconds in, I can give it 3, and in return, it'll give me the velocity, right? It can also work the other way around. We can also go about it backwards and say, okay, when is the velocity going to be negative 12 feet per second, right? Then I can insert negative 12 in for velocity and solve for t. Same thing with position, right? I can give it a specific height and ask when this object, this ball, is going to reach that specific height. So it does feel more straightforward to give it the time and in return get the velocity, or give it the time and get the position. But just know that it can also work the other way around. We can also ask for the time given the velocity, or ask for the time given the height. Okay, next up, let's go ahead and find the derivative again to get to acceleration. So it's the second derivative of height, but it's also the first derivative of velocity. So let's go ahead and find the derivative again. Negative 32t turns into negative 32. And then 64 goes to 0. So that acceleration is the constant acceleration due to gravity. And so that's why it doesn't matter if the t is 2 or 3 or 5, it'll always hold that same acceleration. Okay, so now let's look at number 2 here. Now we're pretty much done with the calculus. We're just using these functions to find the information that we need. How tall is the building? Well, we know that the ball is going to start off at the top of the building. So we can just insert 0 into the position, right? Into the height, right? Wherever the ball is at the beginning is going to be the height of the building. So how high is the ball from the ground?
80.
80. So we know that that's also going to represent the height of the building, 80 feet. Okay, number 3. When does the ball reach maximum height? Okay, so let's figure out what we're trying to solve for. When That means we're solving for what? T, we're looking for T. When the ball reaches maximum height. Okay, so we need to kind of think about this for a moment here. Let's think about this, the path of this ball, right? It's going to be thrown upward and it's going to reach its maximum height and it's going to make its way down. Now, is there some observation that you can make? Okay, this is assuming that we throw the ball straight up in the air. An observation that you can make about a behavior of this ball when it reaches maximum height? It stops for a moment, right? So we know that maximum height, at least for this problem, is going to be associated with when velocity is what? Velocity is 0, right? It's not the case for every problem, but in this problem, we kind of picture that happening, right? It's going to hover for a moment, motionless before it starts its descent down, and that moment of motionless is also going to correspond with maximal height. So what we can do is we can set velocity equal to 0 and solve for t, right? Because when velocity is 0 for this problem, that is the time when we expect maximum height to be reached. Okay, so we're going to solve for t and figure out how long it takes for the ball to reach its maximum height, or how long will it take before the ball experiences a velocity of 0. What's t equal to? 2 seconds, right? So it's going to take 2 seconds before the ball hits a velocity 0, which is therefore maximum height. So now, number 4, related to number 3, what is the maximum height? So how would we go about doing that? Yep. 2 into the of height, yeah, into position, right? Because now we're looking for the maximum height. We're not looking for velocity. We're looking for a position, a height of this ball. And conveniently enough, we have the t value that we need. So 2 gets inserted. Okay, I'll do the calculation for us here. So 2 seconds in, the ball is going to be 144 feet off the ground. Okay. Number 5, how long does it take for the ball to hit the ground? So how long, what are we looking for? Time, okay. For it to hit the ground. So can you correlate that with a specific value? Fine. What else? So when you're on the ground, what's the height? 0. Okay, so we can think of it that way, right? So if I can figure out when the height is 0, then I can solve for t. So 0 equals. Okay, there's a factoring problem here. We can actually factor a negative 16 out of each of the terms. Okay, go through factoring, multiplies to be negative 5, adds up to be negative 4. Factor form, the 16 is not going to matter. We're just going to solve for t. T minus 5 equal to 0, t plus 1 equal to 0, so t equals what? Yep, 5 and negative 1. Okay. Now, sometimes we may be dealing with a quote unquote negative t value. And if that's the case, we'll just go with it. But we're always going to depend on what the problem tells us. The problem is always going to, especially if it's a word problem, it'll always define what the domain is. So in this case, we're talking about t that is greater than or equal to 0. So we have to follow whatever the domain gives us. And because domain is only positive numbers, we're going to remove that t with negative 1, stop part of our domain. Okay, number 6, what's the initial velocity? Okay, what does initial mean?
The beginning.
Beginning, so that's when t is equal to 0. So you want to find out what is the velocity of this ball at 0 seconds. It's as simple as inserting 0 in for t and finding the velocity. Okay, and what's our unit of measure here? Feet per second, right? It's a rate. That positive number indicates the ball is still on its way up, but as soon as we see a negative velocity, we know that the ball is on its way down. Number 7, that's easy as well. Find the velocity of 1, find the velocity of 2. Okay, we already kind of know what velocity of 2 is because we saw that from number 3. Okay, number 3, that's our number 8 is also straightforward. What is the height at 3 seconds? Plug in. All right, I'll do the calculation here. This gives us 128 feet. Okay, number 9. What is the speed when the ball hits the ground? What's something that's related to speed? Velocity. So let's worry about velocity first. Let's look for velocity, and then we can worry about the speed. So let's look for velocity. We'll find v of t when it hits the ground. Do we know how long it takes for the ball to hit the ground?
We're gonna put in 5 for T.
Yeah, so we have that information from number 5, so we'll carry that over. Yeah, so good. Let's find the velocity at 5 seconds, and then we can worry about the speed. So 5 seconds after the ball is thrown, we want to find the velocity because that's when the ball hits the ground. Velocity at impact. Okay, so velocity is negative 96 feet per second, right? Negative 96, it's going downward. So what can we say about speed? It's the positive version, right? So speed is just positive 96. Okay, number 10, that's pretty easy. Doesn't matter what the time is, right? Acceleration is always going to be what?
32.
Negative 32. Okay, now what's the unit of measure? Yeah, feet per second, right? It's the rate of change of velocity. So it's feet per second, but we can clean that up and make it feet per second squared. Okay, put a star next to 11 through 14 because these are the ones that give us the most trouble here. And here, and the one that gives, yeah, so especially 11 and 12. So let me just do number 11 real quick, and then we'll stop. It says find the average velocity in the time interval from 0 to 2. Now, the tricky thing is that this word average. That average velocity is going to force us to use a different formula than the velocity function. We're not asked to find the specific velocity at a moment in time. We're asked to find the average velocity. So just like how I asked you, what's the average velocity, average speed of your road trip? You're taking the slope between 2 points. You're not doing any calculus involved there. So average velocity is simply the change in position divided by the change in time. And what trips a lot of us up is the fact that we see the word velocity, but we're not going to use the velocity function. It's the change in position over change in time. So it's just going to be h of 2 minus h of 0 over 2 minus 0. And I know how easy it is to look at that velocity and try to force the velocity into it. Some students, they take velocity of 0, velocity of 2, or they find the average of the two velocities, or they do change in velocity over change in time. And it's just frustrating, I know, to look at this and not touch the velocity function at all, because that's not the way that we define average velocity. Okay. Okay, good. So we'll pick this up tomorrow. Again, the homework assigned, I'm not going to check until Monday. Welcome for you guys to encourage you guys to try it, but we'll pick this up tomorrow. And we'll finish up 2.2 tomorrow. Okay, someone forget your phones.